Non-destructive, what does that mean? Or non-invasive? I'll use those two words. I exchanged those words. So I'd like to start my talk by explaining, well, non-destructive and non-invasive, to me, they're practically the same. But what it means is you just simply you cannot cut into the fruit. Basically, you use techniques to infer the quality of the fruit. And the purpose of this talk is not to exhaustively describe every single technique, but it's for you guys to be a little bit aware of what's real and what's fake, or what are the type of questions that we need to ask. There's so many equipment manufacturers out there, and there's so many promises of things that supposedly a piece of equipment does, but I believe that after this talk, you can ask the right questions of seeing if that's real. So we'll talk about non-destructive techniques today. So I want to see some hands. If you would look at this fruit, who would eat it? Any of them? I would eat it. So you might bite into it, but you probably won't eat it. The take-home message of this is that external quality attributes are related, of course, to internal quality attributes, but in many cases, they're undetectable. So when, again, going back to a manufacturer, tells you that they have the ability of looking at the internal components and the external components, there are two different techniques that can potentially do that. It's fairly trivial to look at the external part of the fruit, but it's extremely challenging to look at the internal properties of the fruit. So as in this case, this is just an example of a tart cherry that had an infestation, insect infestation, apple browning, avocado, very common, and pineapple translucency. So how do non-destructive techniques, or how do electronic digital sorting systems work? Basically, I can divide this into 5 different components. One is conveying of the product as the unsorted the unsorted product, both good quality, high quality, mid quality, whatever, is conveyed through the second component, sensor-based inspection points, and this is where I will focus the majority of my talk today. And what are the sensors that are available out there? Or what are we using even in state-of-the-art sensors? 3, there has to be a computer. There has to be an algorithm that we've trained beforehand to determine what those measurements are telling us. This is an apple that has a spot in the surface, whatever. We've trained them to do this. So it's very exhaustive. You need to present the piece of equipment or the sensor or the sorting system with all this information for it to be able to make those decisions. 4 is the physical objection or separation of the products. There's many ways of doing that, typically in small fruits or nuts or rice or coffee or whatever you use, compressed air. Other larger fruits can use cups, whatever the world, there's many ways of doing it. And 5 is correctly separating what's bad and what's good. First and foremost, and one of the biggest challenges in this field is the throughput. So this is one example of how the throughput what is the throughput consideration. So just kind of the rule of thumb when we develop these techniques, depending on the size of the fruit, of course, but the throughput is between 40 up to 400, in that range, items per second. So it's much faster than you can, think. So that's kind of the throughput. If it's below that, there's certain pieces of equipment that can, or certain markets that can cater to that. But generally speaking, this needs to happen really fast. So let's look at an example here, just how this works. We have, looks like an orange. Sorry for the color there, but we have a healthy orange, nice and orange. We have a HLB, whoever can say that word, it's a champ, but HLB disease, rust mites and wind scars. And the purpose of this study is in real-time processing, be able to separate between these 4 quality types. Fairly trivial because this is a surface characteristic, so you could basically do it with color. Any change in color was detected or could be detected, but in this particular case, there was a 90% classification rate. So this piece of equipment was able to segregate these 4 qualities with a 90% accuracy, or only around 10% error rate, of around 100 or 5.4 oranges per second. So I just told you the throughput. Is this appropriate? Too slow. So what do? There's multiple lines in many cases. Oh, you hear that? I just mentioned the how do you separate. Those are the cups opening and closing as they're going through the system. The sensors or the cameras are right there, and as the in this case prunes are conveyed, they're automatically sorted. But the way that they've increased the throughput is increasing the number of lines within that sorting line. That's one way, of course, but it's not doable with every single case. In many cases, one sensor, if we're looking at color, is fairly inexpensive, but other cameras can be very, very pricey, so it's not as trivial to just add more lines to it. This is in red. I've marked where a non-destructive sorter could potentially be beneficial. This is how a typical operation plant looks like. There's some pre-sizing. We know that there are sorters that can pre-size. In many cases, there's some hand sorting for external quality. This can also be done fairly straightforward. Electronic sorting also for additional external quality and internal quality attributes. Internal quality attributes are significantly more challenging, but it's doable in certain cases. Then again, it's hand sorted one more time, and these are required by the consumer. So if we could incorporate different techniques within each of these different components, then we could potentially enhance the quality of our product, and not only that, reduce labor costs and so on. So there's many techniques for non-destructive sorting techniques, and I'll mention some today. We have the oldest way of sorting products. You see this all around the world, floating, or where healthier, denser products tend to sink in comparison with products that have void spaces. Infrared, ultraviolet, and near-infrared, color, camera, visible. This is the most common. There's 2D X-ray systems that are commercially available. Computed tomography, that's what I got my PhD on, and it's not commercially available, and I don't see it being commercially available in many years. We have magnetic resonant imaging. There's also some driving forces that are allowing this to happen. Sonic and ultrasonic vibration, and I'll stay out of electronic gnosis and volatiles for the purpose of my talk, because these techniques unfortunately have proven to be unsuccessful at the high throughput rates that we're looking at. Okay? They're successful for certain things, but not at the rates that we needed. This is an example of what happened the first day that I arrived in Michigan. I learned this. These are chestnuts, or castañas, like they say in Italy. For every 10 chestnuts, what was told to me and what I could see after a survey is that around 30% of them were rotten. Typically, it was a mold. So what the industry did over there was they would float this. The sinkers, what we call the sinkers, had higher density and better quality, tend to sink. You would expect that we would be able to eliminate this with that technique. But what we found is that around, if we would float this, in the sinkers, we would find 20% that were still rotten. So what did that tell us? We were storing product that was rotten, it was contaminating others, it was expensive, and the client was dissatisfied. And in the floaters, around 10% were actually healthy. So it was kind of a mix. So we were discarding 10% of our profit. In many cases, that is the profit of the industry. I mean, that's what keeps you alive, 10%. So they were throwing everything away, basically, or at least 10% of it. So they weren't happy with that. And that's when we started looking at alternative means of measuring the internal quality of the chestnuts to increase consumer satisfaction, offer better quality of the product, increase market share, and lessen the complaints. Before I continue, 100% of the methods that I'll talk today, except for floating, rely on the electromagnetic spectrum. And we, as humans, we're very weak. We already know that. But this is what our eye can see. From 380 to 780, if you're extremely healthy. I probably can see half of that. My eyes are not pretty good. There is some people that can see the whole range, but it's atypical. So that's what we mean by computer vision systems or color vision systems, that they can look at light within that range. But now we have the ability of using other techniques and other methods and other sensors that can detect light way beyond that or way below that. That's why we can rely on X-rays to look at the bone structure and so on, and the potential internal quality of product. And others, like infrared, you hear near-infrared spectroscopy, near-infrared hyperspectral imaging, whatever that is, okay? But we still rely, even though it doesn't typically relate directly to the maturity of the product and so on, we rely exclusively on color, in many cases, to look at the quality of the product. Why? Visual appearance is extremely important. It also relates to the development changes in chlorophyll and other pigments, and in some cases, ripeness and maturity. It's not always the case, but generally speaking. And we can also detect some issues like this gloss or browning or achromatic effect of what we can see here in the pineapple. But how can we measure color? I mean, we have a ruler, to measure length, but how can we measure color? What color is this apple? Red. That's very subjective. I mean, you could say red, you could say burning red, a crimson, bright red, whatever. This is not a very objective way of measuring. So we had to develop a technique of how to standardize the measurement of color, and this is what we'll explain here right now. So first, to measure color, you need to have one, light illumination, regardless of what wavelength of that light you're measuring. If you have a near-infrared camera, you need to have an illumination source that is going to generate wavelengths of light within that range, okay? So that's important. One, the type of light. Two, the type of object. How much do you think light goes through matter? Just in the visible range. Any ideas? Not even a millimeter. Almost nothing. What about near-infrared? Everybody tells you that near-infrared is the next best thing. How deep do you think near-infrared can go? 2 millimeters at much. Okay? So if somebody tells you, with my near-infrared system, I can detect the defect on the core of the apple. Is that accurate? With with X-ray, I can potentially do that, okay? Changes in density, that, yes, but not with near-infrared. So that's the type of questions that we need to ask. So, but how do we measure color? There's many, many ways of measuring color. We could talk for hours of how to measure color, but you basically describe color in 3 different components, which are common in the food industry. So you'll look at the L, A, B values. L is a difference between lightness and darkness. B is the difference between yellow and blue, and A is the difference between red and green. And if we, like GPS, if we can find those 3 values, we could exactly pinpoint what color that apple is. So to do that, we have a colorimeter. And this is a device that quantifies the intensity and concentration of color using this color theory model, LAB, where we could see that the lightness, the A and the B values are significantly different between a green and a red tomato. Probably the only ones that are slightly close is that B value. And the reason why is because it's the difference between yellow and blue. But if we look at green and red, an A value of minus 40 and a B value of 42. So big distinction. Okay, so now we can start defining color or describing color. This is where that green tomato will fall. This is where that red tomato will fall in relationship to those coordinates. And yes, we've developed techniques to assess this quite accurately. This technique I developed where we could get asparagus samples, and of course I used a flat panel scanner, but this was translatable to any computer vision system. We would, get these images. These were the original images, and the purpose of this study was to determine which ones were tips, midsections, or bottom sections, because the consumers were complaining that they didn't want this, or at least they would like to have in a cut asparagus bag, they would like to have a ratio of 3 of this for 2 of those, because I like the tips, that's it, see? So that's basically, that's one application. This is highly successful. In this case, we could separate in those 3 like around 92% accuracy. So this is applied already in the industry. If you get cut asparagus, techniques like this are already applied, where we can discern between a tip and a bottom of our asparagus. I'll jump through that, so that it's just another example, where we could do that. Near-infrared, hyperspectral, and multispectral imaging. All those words are going to be thrown at you guys. And they're very confusing. So what is the difference between hyperspectral and multispectral? So let's start with the camera. So this is a hyperspectral image camera. The illumination source could be very similar to the multispectral camera, but so we have the light source, as I said, that's number 1. What would be the number 2 to measure any characteristic? 2 would be the object or the sample. 3, the sensor. So we have this hyperspectral image cameras can acquire continuous set of images. Imagine that you have an array of images at between 367 and 980 nanometers. That's a lot of images to process through. And then each of the different nanometers, you would see different characteristics within that fruit, because the light is absorbed at different levels depending on its characteristics. Okay? So lots and lots of information. Hyperspectral imaging cameras compared to color vision cameras and other methods are extremely expensive. $150,000 a camera. So if we're going to if somebody tells you like we have a hyperspectral imager, well, that's perfect. But if you have 7 lines on that, that's 7 times 150 plus everything else. So not trivial and not cheap. But what about my multispectral? So, they're always asking us, we develop these techniques as engineers, and they always ask us to make them cheaper. That's sad, but whatever. So we always make things cheaper, and that's where multispectral imaging came through. So instead of getting many images or many information from every single wavelength, now we can have narrower bands where we're looking at something that we think is right there, but we have less information. So it's typically between 3 to 10 bands, and the price varies quite significantly. Even further, I've been talking hyperspectral color vision, we have an image. Hyperspectral image, we have an image. Multispectral image, we still have an image at different wavelengths. If we want to simplify this even more, we can grab this one image and average up every single value within that image and get one value. That's the definition of spectroscopy. So we have one single value of color for all of the wavelengths. So we summarize this, and it looks like a spectrum, where in the y-axis, you get the intensity, and in the x-axis, you get all of the wavelengths. And that intensity value is 1. So we went from 1 image to 1 value in summarizing this. This is very typical in sorters. Very typical. This is the typical techniques that they use. Why? Because it's inexpensive, okay? And still fairly accurate. But as we lose all that information, as we make it cheaper and cheaper, we lose a lot of information and accuracy and so on. There's different ways of doing spectroscopy methods. We have refractance, where the light basically hits the object, it reflects in the surface, and then it's captured by the detector. In transmittance, what if we have an apple here? You think the light's going to transmit through an apple? I told you at the beginning, at 2 millimeters. But what if we have a cherry? Yeah, probably. Okay? Some can transmit, but still not all of it will transmit. The majority of it will scatter, and we lose a bunch of information in there. And last but not least, interactance, where you have several sources of light that interact with the product, and you can acquire much more information that way. This was a project that I was in charge of, where we were working in trying to detect the presence of fiber tissue within the carrots. When I was in Guatemala, I never thought the fiber tissue in a carrot was going to be a problem, but apparently this could represent a choking hazard. Okay? So when you do like baby food. So Gerber subsidized this project, very interesting. We were looking at near-infrared hyperspectral imaging. This is one image of thousands that we had. This is one 914 nanometers, 1 point in that spectrum. This is how the images look. You could see that we could somehow detect the difference between non-fiber and fiber. If we look at near-infrared interactance, so we did this modality, we could discern between carrots that had fiber and others that didn't. So it's possible, okay? We also did this with processing tomatoes. This is actually applied right now by Key Technology Imaging Systems. They have one of the few hyperspectral imaging systems that can acquire properties of sugar contents. So in this case, this is what we developed. We had, if you have high levels, long story short, if you have high levels of sugar, when you fry the potatoes, they brown, okay? And this browning is undesirable for the consumer. So we knew that we could, using spectroscopy techniques, we could detect the presence of sugar. Key Technologies took it even further, and they can find the spatial distribution of that sugar. So now they can cut those parts that they don't want, remove them, and use what's useful for them.
So that was like a slice? What was that?
Yes, this is McDonald's. French fries. That's how it goes. So this is the different slices or sliced potatoes. Yes. So it's color coded. The ends had higher levels of sugar. They appeared to be bluish there. The centers, which are red, had lower levels of sugar. So they could come in with a knife and cut this and just fry that part there. High quality. Okay. Very pricey. 2D X-ray, I don't want to go much into it. There is one commercially available system that does 2D X-ray. This were acquired by that system. These are chestnuts. We developed computed tomography techniques, inline computed tomography techniques that could do this. And compared with 2D X-ray, which is one image. CT is multiple images, multiple X-rays at around that same item. We could detect void spaces down to the millimeter level using computed tomography. Unfortunately, too expensive, still not commercially available. Here are my sorters. What did I say? White was healthy. Is that right? Black or gray or dark is rotten or void spaces. Tell me when you see rotten chestnuts. Oh, there they come. Look at that. So the computer has the ability of doing this at a very, very, very fast pace. Okay? You just became digital sorters with me right now. Okay? 2D X-ray images, difference between computer tomography images. And I'll just fly through these ones just because I 5 years of my life I did this, so what do you expect to have a lot of images like that, okay? I'll run through this for the sake of time because I want to get to this system right here. Inline non-destructive maturity sensing. We have 2 light sources, 1 sensor. What modality is it? Reflectance, interactance, or transmittance? No reflectance. Interactance. It's not transmittance for sure. So you're using interactance methods to quantify or online classify the maturity of tomatoes. This is what the machine did. It classified this. Oh, by the way, this is a near-infrared system. They can look at light at between, if I'm not mistaken, around 650. So it takes a little bit of the color up to 1200 nanometers. So it acquires a spectrum, and it sorted it in three different categories: immature, intermediate, and advanced. I can't tell the difference between groups. I've been corrected many times, but I've also told you that I'm half blind, okay? But I couldn't tell if there's a difference between this one, and that one. But the machine said, yes, I consider this to be immature, this intermediate, and this to be much more mature. 7 days later, this is what happened. So it's the same tomatoes, okay? These tomatoes that were classified as immature, 72% were still green 7 days later. The opposite end, that were considered, advanced, sorry for the colors there, but advanced, matured, 0% were green. So this could help you, either, redirect your product, store it appropriately. The world is the limit at that point. So the conclusion is that online systems can classify this. In this case, this was 80 to 85% accuracy. There's also handheld measurements that could be done. Probably not as accurate, but also available. And last but not least, these are commercially available equipments. You will have access to this list, which is changing every day. Suddenly, Grifa bought, Best bought, I don't know, everybody buys each other and whatever. So this is probably very inaccurate 3 years from now, but close enough. So this is what's commercially available. And with that, drinks are not on me, but they're out there. We'll see you later.